Welcome to this NPTEL lecture on horn antenna. We have seen in the previous lecture the open ended waveguide and found that its directivity is 3.5, which may be better than dipole, but it is not sufficient. So, we want higher directivity. So, for that the idea is if the aperture is flared, then we can get a much larger aperture opening. So, our area of the aperture in terms of lambda naught will be higher, and so we may be able to get higher gain. So, the first of that type is called a horn, which is a H plane horn. You can see the the picture that H plane horn. Actually, this was the waveguide. Now, we have seen that the H field that is in this plane. So, this is the, I can say, H plane of the waveguide, or if we go back to the rectangular waveguide, that will be better. So, you know that the electric field is in this direction. So, magnetic field is in this plane, this direction. So, that means we can say that xz plane, that is the H plane of the rectangular structures. So, if that gets flared, so you see that this one is getting flared in a horn. This is called H plane horn. So, if you see the side view, this is the top view. If you see the side view, so the rectangular waveguide, so its broader dimension A. Now, suddenly from here it is getting flared. So, that flaring is done by an angle, and if you project these two lines, they meet at a hypothetical point. We will call this apex of the horn, okay, this point. So, in this point the flaring is making an angle psi, the flare angle. So, this distance from this apex to this end, that we are calling R2, and if we go straight from this apex to the center of the horn aperture, that we are calling R1. Now, actually cylindrical waveguide, the rectangular waveguide was bringing T10 mode. Now, suddenly when it starts getting flared, a line source is created here. So, a cylindrical wavefront is radiated inside this, from this flaring start point to the flaring end point. So, here is a cylindrical phase front with a circular phase distribution. So, the point is, obviously here you see that at the aperture the phase at this extreme point is different from the phase at the center. So, there is a phase error here, because the idea of any aperture illumination is that if we can illuminate the aperture with an uniform phase, then we get the maximum radiation. Directivity is maximum at the both side point. So, here this thing will restrict or reduce the directivity, but we are getting much larger aperture. So, these two effects actually counterposes. The larger aperture makes the directivity more, and this error tries to minimize that. Now, actually there is a restriction that you should not flare very much, so that this phase error that you are committing here, that means this much phase error, that should not go beyond a point. Typically for H plane horns, that restriction is the phase error should not exceed plus minus pi by 4 at the sides of the aperture. That means phase error from this point to this point, that means that should not exceed pi by 4. Similarly, here also it should not exceed pi by 4. So, that is the restriction. So, here I show you a real H plane horn. You see this was the rectangular waveguide gets connected here. So, this side is a rectangular waveguide structure. It is a rectangular waveguide. It is a rectangular waveguide, and this you are saying that H plane is getting flared. The electric field is this directed, the magnetic field is going inside. So, this plane, this xz plane is getting flared, and you see from here it is getting a flare of this. Apex is something here. If I extend this point and this point, I get an apex here. So, with respect to that apex, we are now discussing. So, looking into this figure, we can say that we can easily calculate what is the phase error and what is the condition that that phase error should be less than pi by 4. So, we can write that the phase error will be k naught R2 minus R1 should be less than equal to pi by 4. Now, what is R1? I will try to introduce the flare angle psi. So, R1 is nothing but R2 cos psi by 2, and what is A dashed? A dashed is, A dash means the total broad dimension of the horn aperture, that is 2 R2 sin phi by 2 psi by 2. So, now you can easily find out that what is the angle that I need. So, if you put that this thing should be less than by 4, that gives you that tan psi by 4 should be less than equal to lambda naught by 4 A dashed. So, maximum value of psi is limited, because if you do not do that, then you disturb the phase distribution at the aperture. So, it is seen that maximum value of the flare angle, that is inversely proportional to the horn's dimension, horn size. So, actually in order to have we said that our main motivation for coming to horn is we want a large aperture. So, if we want to have a large aperture opening, the flare angle will be small, resulting in a very long and bulky horns. So, this is the disadvantage of horns, that they becomes very bulky. So, that is why with the horn we can produce only a modest gain. Actually, if you want to produce very higher gains, horn is not used, then a reflector antenna is used to have more gain. That is why you see satellite people or radiometry people, ultimately they use a dish antenna for that, dish reflector for that, because horn it will be very bulky if you want to have that whole thing gain by the horn. Also its size, etc., and its weight, because this is fully a metallic structure. So, that is why generally for practical horns we do not have the aperture sizes more than 10 lambda. So, even for a 10 lambda thing, the horn will be close to 100 wavelength long. Now, we can say that when the phase variation is restricted in this manner, so that we can neglect the phase variation in the aperture field. The aperture field may be assumed to the same as that for dominant T10 mode feeding the horn. So, we can write that the aperture field, that will be A y E0 cos pi x by a dashed. Please remember this is a dashed here, this is for x less than equal to a dash by 2 and y less than equal to b by 2. So, we can easily find out that what will be the far field. In this case there will not be any phi component because we do not have any x component in the field, that we have already seen in case of open ended waveguide. So, E theta will be j k naught a dash b E naught by 4 r e to the power minus j k naught r sin phi sinc v cos u by pi by 2 whole square minus u square, where as before v is equal to k naught b by 2 sin theta sin phi and u is equal to k naught a dashed by 2 sin theta cos phi, and beta, where is beta, is k naught square minus pi square by a dashed square whole to the power half. So, you can see from here, since a dashed is large, so beta is almost equal to k naught, and d, the directivity of the horn, d is 64. This is I am writing from open ended waveguide, only a is replaced by a dashed. So, a dash b by k naught lambda naught square. So, this with putting this k naught value etcetera, you get 10.2 a dash b by lambda naught square. So, this is your physical area, electrical effective electrical physical area. So, actually directivity is 10 times that you are getting by this horn. And so, you remember that in microwave frequencies the gain of horn is essentially equal to the directivity, as losses are negligible. Now, if the horn length is fixed, that means if this length is fixed, but I want to have more higher gain, then it can be obtained by increasing the flare angle to some extent, that will cross that pi by 4 restriction on the phase error, but with the increase in the aperture, because if I increase the flare angle, aperture will increase. So, somewhat the gain that I get more, that somehow compensates the loss in the phase error. So, people have analyzed this and found that it is possible to get the maximum gain is obtained by increasing the aperture with a dashed until a phase error of 0.75 pi, that means 3 by 4 pi. That time we are saying pi by 4, now we are saying that 3 by 4 pi, up to that you can go. So, the gain that will be from the formula, now gain will be reduced, but that reduction will be the so I can say that new gain will be for the H plane horn will be 10.2 divided by 1.3. Actually, this phase error makes the gain reduced by a factor of 1.3 a dash b by lambda naught square. Then you can say why we are choosing, because I am increasing the a dashed. So, by that the maximum gain is obtained. So, this is the formula that is generally used. So, if I go up to this 0.75 pi. Okay. So, this is the H plane horn. The next one we see is, this is a graph. You can see that how flare angle changes the A dash, there is a point. So, if I go on increasing the flare angle, then you get that A dash gets increased, but it is better that if you have the larger ones, then flare angle should be kept at a optimum value. Now, the next one is our E plane horn. So, let us see the E plane horn, that you see the graph. Here the E plane, the electric field is this directed, that means this y directed. So, flaring is done in the y. Here it is shown that E and H. So, E is here. So, flaring is here, that means here A is kept constant, the broad dimension, the narrow dimension B, that from B it gets flared to B dashed. Okay. You can see this is an example of a E plane horn. You can see this is the rectangular waveguide side, this is the other side. You see from the side, if you see that E plane is getting flared, or from the side you see that this is the E plane. So, E plane is getting flared, the other one is kept constant. So, this is an example of a E plane horn. Now, the same consideration as we have done there applies here. So, here the formula for directivity is 10.2 A B dashed by lambda naught square. Again, people have found that if horn length is fixed, I want to increase gain somehow, then I can violate that pi by 4 thing and go up to here. I cannot go up to that 3 by 4 pi or 0.75 pi. Here we can go only up to 0.5 pi, that means pi by 2 only. Instead of pi by 4 phase error, I can go up to pi by 4. So, why it is so? Why in H plane I can go up to 3 by 4 pi and in E plane I can go only up to pi by 2? The reason is in the H aperture field for a rectangular waveguide, that goes to 0 at the sides of the aperture in the H plane, whereas in the E plane the aperture field is constant. So, that is why here you cannot go beyond a point, because then you will disturb much, but there you have a chance, because at the ends it is going to 0. So, you have more liberty in the H plane things. Okay. And here also, if you do this, how much reduction in the gain you suffer, that is, so since you are going less, you will suffer less. So, 10.2 here instead of 1.3 it is 1.25 A dashed A B dashed by lambda naught square. Okay. So, this is the E plane horn. Then people thought that to obviously a better thing will be that if both E and H plane things are flared like this. This I think all of you have seen many times, that this is called pyramidal horn. So, in both direction you see that this plane also is flared, this plane also is flared. This is, so this is this flaring, this bottom one, if this one you see, this flaring is the H plane flaring, this flaring is the E plane flaring, both are flared. But remember the very important point, that when it was constructed, you see from the top that from the same point when the E plane flaring started, the H plane flaring also started from the same point. This is one of the things that we will have to keep in mind while designing. So, This is a horn made by Seco, one of the Ghaziabad companies. So, these are all Indian made things. So, you can see the graph, you can see the pyramidal horn. So, in both the directions you have flared. So, ultimately your aperture is A dashed by B dashed. Now, in order to have a negligible phase error in the flare angle in both planes should satisfy the phase error condition, that tan psi E or H I am writing. So, all these to be together satisfied. Obviously, if I satisfy, generally A dashed is larger than B dashed. So, if I satisfy these, this gets automatically satisfied. Okay. So, the radiated field and directivity, they are also same as E or H plane horns, with A replaced by A dashed and B replaced by B dashed. So, for a fixed length horn, if I am allowed to do maximum gain thing, then people do that. For H plane, they suffer that 0.75 pi phase error, and in the E plane suffer that. So, for that, what will be the gain of a pyramidal horn? I can write 10.2, then divided by 1.3 into 1.25, then A dashed B dashed by lambda naught square. So, this becomes actually this famous formula 6.4 A dashed B dashed by lambda naught square. This is the gain of a horn, pyramidal horn. So, pyramidal horns are used for, one is they are varying in standard gain horn. You will see that in antenna measurement etc., or various measurements, we want a standard gain. Now, horns, horn is one antenna, horn, dipole etc., but horn gives good value of gain. So, horn we know from its geometry, I can tell what is the gain. So, that is why standard gain horns are made always from these pyramidal horns, because any gain can be obtained by manipulating the length. And so, also for comparison of gain of an unknown antenna, these gains, these pyramidal horns are used. That is why in all antenna laboratories you will see at least these pyramidal horns, because they give standard gains. Then small pyramidal horns are used as feed horns, that we will see later, that for paraboidal reflector or the dish antenna. In your homes, the DTH service, there also you will see that there is a dish, but you see that near that there is always sitting a horn antenna. So, that may be a circular horn, that may be a rectangular horn, but there is always a horn. So, that is also another use. That means, in that paraboidal reflector system, it is called a feed horn. So, as a feed horn also horns are used, and also in large array antennas, for feeds etc., horn is used. Now, since it is so important, particularly for us, we in laboratories, this is important. So, I will now spend some time on the design of the horn, because that design is very important. So, you see that here will be some geometries, that let us see the horn. Here you see that first I am taking a flare in the H plane. So, flare in the E plane. So, B is getting flared to B dashed. So, this is my B dashed, and let me name it that, let us say the if I the apex, let me call it A. This point is the apex of the horn A. Now, so the point where the flaring started, let me call it B. On this line, this point is C, and this one is called this point on the aperture, let me call D, and this point at the top, let me call E. So, here you can see easily that I can, from geometry I can always write AB by AD is equal to AB by AD. You all agree that these are all similar triangles. So, AB by AD is equal to BC by DE. I can easily write this. And so, what is AB? So, AB will be, before that also let me have another drawing. Of the same H plane horn. This is my B dashed and this is my apex, and we will call this flared thing rho E, and this one from here to here rho 1. Okay. Now, actually what I am trying to do, I am trying to find from the apex to the flaring point what is the distance. This one actually I will call this one is my B extra. So, this is my actually, that means because these are from outside seen, this is an hypothetical point. So, what is this extra point that I am trying to find out. So, I have given this thing, the angle let me give, this angle is psi E, I am saying because it is an E plane horn, and I will also say that means the flaring that has taken place for an length P, that means from here to here the length is P. Please remember that rho 1 is from here to apex. So, I can say that rho 1 minus B extra will be P, because I will have to see that when a horn actually is fabricated, the PE, the physical this length should be equal to in the other plane PH, because that is the constraint for designing a horn, that physically they should be same. That means, this distance in this distance and this distance they should be same, otherwise it cannot be fabricated. So, I am actually trying to calculate P from the given this thing. So, that is why here now I can put what is AB, AB is equal to AD, AD means from here you can see rho 1 into, you can see that B by 2 by B dashed by 2. So, I can now write that what will be P, P is equal to BD, you see BD, and that means AD minus AB, and that means rho 1 minus B by B dashed. So, now rho 1 is also generally not given for any horn. So, I will have to relate it with the flare angle. So, now I can write tan psi E by 2 is equal to B by 2 by B extra, and that is nothing but B dashed by 2 by rho 1. So, from here you can find B extra is B rho 1 by B dashed. So, P becomes rho 1 minus B extra, and that if you do, you get B dashed minus B by B dashed over rho E square minus B dashed square by 4. So, finally, people write it as B dashed minus B rho E by B dashed square minus 1/4 to the power half. So, this is okay. Now, I will do what is the same thing for H plane horn. So, there also the diagram is this. I have this. So, this is rho H, this is rho 2, and this is P H, and this is this whole thing is I H. This is A dashed and this is A. So, again from the similar thing I can say P H will be A dashed minus A rho H by A dashed whole square minus 1 by 4th half. And to be physically construct a horn, we require P should be equal to P H. Physically constructible, I can say. Okay. So, let us take an example that a pyramidal horn has this dimension. A dashed is 5.5 lambda, B dashed is 2.75 lambda, lambda or lambda naught, whatever you say. A is 0.5 lambda naught, B is 0.25 lambda naught, rho 1 is equal to rho 2 is equal to 6 lambda naught. Check to see if such a horn can be constructed physically. So, what is the first part? You can directly put the formulas, but it is better that you find out rho E and rho H first, because from the geometry it is easy to understand what is rho H. Rho H is, since rho 1, rho 2 is given, which is always it will not be given, but in this case given means. So, I can say that this is the rho H is the hypotenuse of this right angle triangle. So, from that I can easily find out rho E and rho H. So, rho E will be, you will see that it will be 6.1 155 lambda naught, and similarly rho h will be 6.6 lambda naught. So, once you get rho e, you see the expressions, because since you know b dash b rho e also you found out, you can easily get p from here. Similarly, from the other equation you get pH, check whether they are equal. So, you will see that Pe becomes 5.454 lambda naught and pH is 5.454 lambda naught. So, the horn can be constructed physically. So, this is the first check any designer should make, that suppose this is given this, but I will say that this is a middle part of the design, because no specifier does not know all these things. Actual, suppose some other engineer, suppose a transmitter system engineer said that okay, you construct a horn of this much gain. So, generally unless and until only a microwave engineer can give you this type of thing. So, before that actual design is the gain should be specified. You will have to check that what I require. So, that will take up in the next lecture, that what is the design equation of the horn. Okay. Thank you.